This is the Lewis structure of nitrogen. How do we calculate the formal charge on each nitrogen atom? Well, we take the group number, nitrogen, so the formal, let's call this atom A and this atom B. So the formal charge for Na is going to be the group number of nitrogen, which is 5, right? Nitrogen is in group 5, minus half the number of bonding electrons. Now, I've got how many bonding electrons here? 6. So it's going to be half of that, minus the number of lone pair electrons, which in this case is 2. I've drawn this as a line here, right? Equals what? 0. The formal charge on these two atoms is 0. And that's what you would expect, because it's a perfectly covalent molecule. Now let's come back to this example of the CH1001 that I drew here earlier. Let's take this Lewis structure down here and calculate the formal charges on each atom. What is the formal charge on this carbon atom? Well, carbon is in group 4, right? Minus half the number of bonding electrons. How many bonding electrons attached to that carbon? 8. 2, 4, 6, 8. Minus what? The number of lone pair electrons on carbon. How many are there? 0. So what's the formal charge on that carbon atom? 0. Well, what about this oxygen atom here, this guy? Well, it's going to be 6 minus a half of 2 minus 6. Because there's 6 lone pair electrons equals what? Minus 1. You see how this works? This guy is also going to be minus 1. And this guy is going to be 0. Now that's the distribution of the formal charges in that Lewis structure. 0, minus 1, minus 1, 0. Notice that if I sum the formal charges of all the atoms in the Lewis structure, what do I get? Minus 2. And what is minus 2? Minus 2 is the charge of the whole thing. That's the thing. If you sum all the formal charges in a Lewis structure, you should get the charge of the whole ion, or the entity. Right? It's possible that you can have something that's neutral, where you have plus and minus formal charges that cancel each other out. But that's the way that you can check that you've calculated formal charge correctly. Formal charge is very important. You should practice this. You should be able to do this. Here I have the example of ozone, right? Ozone, here are 2 Lewis structures of ozone, and you have a plus and a minus formal charge. If you sum those two together, of course, you get 0. Ozone, O3, is a neutral compound. So formal charge is a reflection, if you will, and a way that we can sort of quantify and understand asymmetry in bonding in terms of polarity. I now come to a very important concept of resonance. Now, resonance is this idea, and I think a lot of students struggle understanding this, but resonance is, let's come back to this example here. Well, actually, let's look at this example on the slide here. That is the Lewis structure of NO3-, the nitrate. Now, notice there's 3 different Lewis structures for the nitrate ion. One guy could draw the Lewis structure in this way. Another guy could draw the Lewis structure in this way. And another guy could draw the Lewis structure in that way. All 3 Lewis structures are correct. Why? Because all 3 of those Lewis structures for the NO3- ion, the nitrate ion, fulfill all the rules, the octet rule, etc. But there's 3 of them. In this one, I've got a double bond to the left. Here, the double bond is pointing up, and there, the double bond is pointing to the right. Which one is correct? All of them. And that's what resonance is. Resonance is you take all the possible correct Lewis structures of a molecule and you fuse them together, and sort of the combination of all of those Lewis structures is a reflection of that entity, that molecule, that species, that ion. So let's unpack this a bit. If I were to ask you to describe, based on what I've just said, what the bond between a nitrogen and an oxygen atom is it a single or a double bond? So that's the question. In a nitrate ion, is the bond between a nitrogen and an oxygen atom a single or a double bond? What would you say?
One half or something like that. It's not one full bond.
Correct.
A partial bond. 1 and a partial.
1 and a third, let's say. Because, exactly, very good. Because there are 3 resonance structures, And sort of you have sort of a double bond there, but there it's a single bond, and there it's a single bond. So, and the same for those. In fact, all three nitrogen-oxygen bonds are identical, but they're neither a single nor a double bond. They're somewhere in between, because resonance dictates that we've got to take all of those and fuse them together. And here are some other examples. SO2 has two resonance structures, and this is the nitrite ion. Again, if you draw the Lewis formulae for that, you'll have two resonance structures. And I think understanding what resonance is very important, and I like these two analogies. If you were to make orange paint, well, how do you make it? You take red paint, and you mix it with yellow paint, and you get orange paint. Okay? Orange paint is the resonance of red and yellow. So if you think about this analogy, orange paint is actually, you would represent it like this, with a double-headed arrow. That is orange paint. It is the resonance hybrid of those two Lewis structures, if you will, the red and the yellow. And that's what resonance is. And let's unpack this a bit more. Orange paint is not 1 minute red, and then the next minute yellow, and then red again, and then yellow. It doesn't jump from one color to the other. It is all the time a combination of those two. In the same way that NO3 minus is a combination of all three of those resonance structures. Another analogy is a mule, right? This is if you cross a horse and a donkey, you get this guy here. Right? A mule is a combination of a horse and a donkey, right? It is the resonance of those two animals. And so is NO3 minus is a resonance of these three animals fused together. Yes, so it has a characteristic. The overall, the way to understand a nitrate ion is it's got characteristics of all three of those, yes.
Just to come back quickly to the formal charge calculation, doesn't this affect the number of bonds then? It's not a double bond, it's not a single bond. And then since it's all a resonance?
Oh, very good question, very good question. You're saying if I have different resonance structures, the formal charges in one resonance structure is going to be different to another. Yes, that's absolutely right. So here you'll have a minus there and a minus there, and a plus there. Here the minuses will be, so the formal charges will move around. You're absolutely right, depending on how you draw the resonance structure. But within each resonance structure, if you add the formal charges up, you're going to end up with a minus. So the formal charges do move around, that's correct.
But I learned in my school that there's also a possibility, since they're resonant, there's a possibility to just draw like a partial bond, so one
Correct.
line and a dotted line.
Correct.
And in that case, then there is no formal charge then.
That's absolutely correct. You can draw it like this, that's 100% correct. This is how you could draw it, to show that it's sort of delocalized. In that case, you're right, there would be no formal charges. But if you draw it as discrete so what you're actually drawing is this is the overall picture. This is like the orange paint, right? What I'm drawing is of the three guys that make up the overall picture. So the dotted line representation here is the overall, we call this the overall resonance hybrid. It is the combination of those structures. So yes, you can do that too. In that case, there will be no formal charges in these atoms, whereas here I will have formal charges. So I think the way to think about it, the orange paint analogy is something that I always use, or the mule. These are classic ways to explain resonance to students, because students think that if I take sodium carbonate and I dissolve it, that you have these different resonance structures of the nitrate, and that if you sort of look at it, that they bounce around, but they don't. It's just a combination of those resonance structures. Okay. So there are exceptions to this, to the octet rule that we've been talking about. The first exception is radicals. We have species in nature that have unpaired electrons. Here we have, for example, a methyl radical. This is a nitrosyl radical. These are, and this is a hydroxy radical. These are species that are very reactive. They have unpaired electrons, and in fact, they cause a lot of damage to tissue and DNA because they basically tear through molecules looking for an unpaired electron with which to get married to. They're very very reactive species radicals. They disobey the octet rule because there's no way that you can get 8 electrons out of that guy there. They're very reactive.
How do they form?
Well, typically, one way that they've formed is by photolytic reactions. For example, if you take hydrogen peroxide, it breaks down first into hydroxy radicals, for example. But there's lots of other mechanisms by which radicals are formed. But one of the typical ones is with light. Okay, and the second exception are incomplete octets. Now, forget about what I've drawn here at the bottom. I think this is just going to confuse everyone. But what I'd like to say is that for beryllium, boron, and aluminium compounds, and also for hydrogen, as we've seen, these elements typically have in their compounds less than 8 electrons, typically 6. So for beryllium, you'd have typically 4, but for boron and aluminium, you would have only 6 electrons around the central atom. And no matter what you do, you can't fix that situation. This is an example. Here I have boron trifluoride. This is the Lewis structure. Now, if you look at this Lewis structure representation of BF3, you'll notice that the boron atom has how many valence electrons around it? Only 6. That is a deviation from the octet rule. So what do? Well, our knee-jerk reaction is to try and remedy it by converting one of these lone pairs into a bonding pair. So we'd end up with something that looks like that. Now this would remedy the situation, and we would end up with 8 valence electrons around all atoms. The problem is that for boron and aluminium compounds, the problem here is that fluorine would never ever do that. Fluorine would never give up one of its lone pairs to form a bonding pair. Why?
Because of its very high electronegativity.
Correct. It would never do this. So basically the fluorine, so this is an interesting case. The boron atom is electron deficient. The boron atom only has 6 electrons around it. It's hungry for electrons, right? It wants 8 electrons like everyone else. But it only has 6. The fluorine has electrons sitting there, but is not willing to give them away because it's too electronegative. The fluorine is selfish and holds on to its electrons. And what you end up with is this. This is the structure of boron trifluoride, and you only have 6 electrons around boron, and aluminium compounds tend to do the same thing. And these are examples of compounds that deviate from the octet rule. No matter what you do, you can't fix the situation, because this would never happen, never ever. You would never end up with a plus formal charge on fluorine and a double bond like that. Forget it. But so these two Lewis structures here are not going to happen, and that's basically the structure of boron trifluoride.
And why like the further left one, right one, sorry,
this
one
one?
work?
Well, that one would make the situation even worse, wouldn't it, for the boron? Because now you've gone from 6 electrons to only 4, and a plus formal charge on boron. I mean, that's even worse than what we have there. So you've now taken electrons away from the boron, and I mean, what you've ended up with is a situation that's infinitely worse for boron. So the boron would not go for that, right? So this is the most stable situation. Although the boron is unhappy, there's nothing that he can do about it. What's interesting with these compounds is if you react them with something that has a lone pair, for example OH-, it would go and sit on the boron. Because the boron, if you actually look at the structure of these things, for boron trifluoride, it looks like this. If you draw it in 3-dimensional space, it's flat as a pancake, right? Like this. This wedged line means that this is draw coming out the plane of the board. This is going back in. And if you look at the structure, you have basically a p orbital on the boron, a vacant p orbital. And so if you take anything that has a lone pair, it goes and just donates itself into that orbital. And then the boron is happy. So this is again something that I discussed in the fall in the 2000 course. These are very important compounds. They're very strong, what we call Lewis acids. Anyway, that's a deviation from the octet rule. Now let's now look at other deviations. If I have elements that are in a high Well, higher than the second period in the periodic table, so like chlorine, phosphorus, sulfur, silicon, etc., those elements, if you look at the electronic structure, have access to d orbitals. Okay? And because they have access to d orbitals, they can undergo something called an expansion of the octet. They can accommodate more than 8 electrons around the valence shell. Now, before I continue, what I'm telling you now is strictly speaking incorrect, okay? Because calculations have shown that main group elements do not actually undergo an expansion of the octet. So what I'm actually teaching you is not really correct. According to very recent, well not that recent, but about 20 years ago, scientists uncovered this. But it's a very good model to explain bonding for heavier elements. So we're going to stick to it. But it's a model, and chemistry is about models, understanding nature. So it's okay if I use this model, although it's not strictly speaking correct. Point is, for the purposes of this course, if you have a heavy element that is in, for example, phosphorus, silicon, sulfur, whatever, that is in a higher period, higher than the second period, it has access to the orbitals and can undergo an expansion of the octet. Let's look at some examples. If I draw the Lewis structure of phosphorus trichloride, I will end up with something like that. That's perfectly acceptable. Every atom has 8 electrons around it. But phosphorus pentachloride exists in nature, and well, not necessarily in nature, but you can synthesize it. And if I draw the Lewis structure of that, I end up with something that looks like this. Now, what's the problem there? The problem is that the phosphorus has 10 valence electrons around it. This is a violation of the octet rule. But it's okay, because phosphorus is in the third period, it has d orbitals, which we can invoke in the in principle. In principle, it doesn't really happen, but this is a model. We can invoke these orbitals in bonding, and we can undergo an expansion of the octet and get something like that. And even sulfur hexafluoride, for example, also exists. And if I draw the Lewis structure of sulfur hexafluoride, I end up with something that looks like that. Okay, a sulfur with, in fact, 12 bonding electrons around the central atom, which is pretty extreme. These are examples of compounds that violate the, well, not the first one, but the second two, that violate the octet rule because they have access to the orbitals. And that's the hand-waving arguments I'm going to use for now. Okay?
I have a question.
Yes.
So you said that recently this has been proven incorrect,
Correct.
even though it's still taught as a model.
Correct.
So
Which is fine, because chemistry is all
Yeah.
about models, yes.
Correct. So what is the new discovery?
Well, it's a good question. So in fact, let's pause and reflect for a moment. So let's take phosphorus pentachloride. Now, that's violating the octet rule. How could I draw a Lewis structure of that guy in a way that it does not violate the octet rule? And this is how I used to teach it in Germany. Because at German universities, they don't teach it like this. They say there's no violation of the octet rule, it's always obeyed. Right? In English-speaking countries, they teach it still like this, so, you know, depends where you are in the world. But there's a way to draw the phosphorus pentachloride in a way that it does not violate the octet rule. How would I do that?
Is it like something called hybridization or something?
Hybridization?
Yeah.
Well, hybridization is something else that's related to this, but basically I've got 10 valence electrons there, so I could, if I wanted to, stick to the octet rule rigorously, and, religiously. I could draw it like this. So what I've basically done is I've just noticed the phosphorus has 8 valence electrons around it. It's not violated the octet rule. I've just made one of the phosphorus-chlorine bonds into an ionic bond and put a plus formal charge on the phosphorus. Now that doesn't violate the octet rule, and that is a perfectly reasonable representation of phosphorus pentachloride.
And it's a resonance.
Correct, and if you draw then all the resonance structures, there'd be, the minus charge would be delocalized throughout. So that is a way that I can, and this is in fact the more correct way.
And this is real.
This is more, well, it's a better approximation of reality.
Yes, okay.
Because the nice thing about representing it this way is that it shows that there's some ionic character in the phosphorus-chlorine bond, right? Which there is. Now, the way that it's represented here doesn't show that. For the purposes of this course, I just want you to be aware of this, right? But this is what we're going to stick to. We're going to stick to the extended octet because that's anyway a model, and it's described like that in Silverberg, and in most countries they still teach it like that because it's just a model on the way to something better. Chemistry is not about achieving some point where you understand everything. It's about having models, and as we go along, we improve our understanding. So this is a perfectly acceptable model. This is a better reflection of reality, because here we don't violate the octet rule. Now let's move on. We have to move on, okay?
Thank you.
Now, the last thing I want to talk about today is VSEPR theory, valence shell electron pair repulsion theory. And I see we only have 10 minutes. Well, we have a task on this. Now, VSEPR theory is basically a way that we can take the Lewis structure that we've drawn, and from that predict the shape of the molecule, okay? And the way that this works is we basically position bonding and lone pairs in such a way that they as far away from each other in space as possible, and based on what we end up with, we can actually predict the shape of the molecule, okay, which is very cool. Now, VSEPR stands for valence shell electron pair repulsion, and it's a very robust theory for simple molecules. Of course, it breaks down when you start working with transition metals and stuff, but it's pretty robust. And essentially, what we're basically doing is we're positioning bonding and lone pairs around, it's all about what's happening around the central atom. That's going to dictate the geometry. Let's look at these three examples. I have methane, ammonia, and water. Now methane, that's the Lewis